So, good evening, friends. Today we are here to the last talk on GW at home. The talk is going to be on laser interferometers. So, I'm going to give you an overview about laser interferometers, how laser interferometers have been ubiquitous for all fundamental measurements and are a precision device in themselves. And LIGO, which is a laser interferometer for gravitational observation, is the ultimate in terms of interferometer design and execution. It's at the extremes of any interferometer. Interferometer tabletop size itself is difficult to align and maintain, and leave alone a 4-kilometer size interferometer of the LIGO style. So let me start with my slides. The plan of my talk is to give you an idea about interferometry and cover various topics on what different types of interferometers are, a brief slide on each of them, just to give you an idea about the various flavors of interferometers. A couple of slides on interferometers and fundamental measurements. So just touch upon them. Most of them you'll be aware historically. And then we'll move on to gravitational wave detection and why a Michelson interferometer is a good gravitational wave detector. And then I'll try to give you a schematic picture of the advanced LIGO detector, its optical configuration, the interferometer's optical configuration. And last but not the least, I'll try to give you a brief overview about the current status of the LIGO-India Project, which is a project for setting up a kilometer scale detector, identical to the LIGO detectors in the US, in India, as part of a global network of gravitational detectors. As most of you would know, interference essentially happens because light does behave like a wave. And the Young's double slit experiment is a classic example of earlier 18th century scientists trying to prove that light is a wave. So this is an example of wavefront division multiplexing. If you choose two parts of a wavefront and they have spatial coherence, you'll have interference. And the interference essentially comes because there is a relative phase error between the two waves as they propagate out due to the Huygens constant. And this high phi is the one that leads to the intensity modulation. And the mod of that gives you the intensity modulation as amplitude. And so interference happens irrespective of whatever is the properties of the beam. Usually when we discuss interferometry, people come up with this idea that we need to have two beams of exactly the same frequency, same phase relationship, same polarization, same ultra-narrow line width, good coherence and all that. These are true if you want to get visible stationary fringes in time. But interference happens irrespective of what you do. Even if you have two wavelengths of light at different frequencies, they do interfere, but the beat frequency is so high that you cannot detect it with any normal detector, because usually your bandwidth is limited to a few gigahertz, and that's the maximum beat frequency that you can detect. So usually the special properties that you ascribe to light if you want to see interference, that is similar amplitudes, same polarization state, and same frequency and same phase constant phase relationship, is for visible stationary fringes. Otherwise, interference is a fundamental phenomenon. It's just the superposition of the electric field of the electromagnetic radiation. So this is a typical equation that you get out when you have two plane waves of good coherence interfering to produce interference pattern. The interference pattern has a cos square function, and which is modulated because of the phase variation between them. And we'll see that further. So this was two-beam interference, and you would also hear about multi-beam interference, which happens when a couple of beams bounce back and forth in a pane of glass, like an echelon, or similar to the Michelson experiment with diffuse lighting. And here, part of the beam is reflected and undergoes multiple reflection, and an ensemble of beams on either side interfere and produce an interference pattern. And this is called multi-beam interference pattern. So the two-beam interference pattern, the best example of that is the Michelson Interferometer, which is a LIGO interferometer. And the multi-beam interference is the Fabry-Perot Interferometer, which is an enhancement that's used in the arms. We'll come to that. So the multi-beam interference is written as a series expansion, and so that can be reduced to the interference pattern equation in the last. So that is a summation over the series of reflections as the it goes. And the total round trip time, this is denoted by a factor called finesse. So the moment we talk about interference or interferometer, or for that matter, two-beam or multi-beam, the idea of coherence comes to mind. And the coherence essentially is a constant phase relationship between the various parts of a wavefront. both across the wavefront, then it's called spatial wavefront, spatial coherence. And if it's in time, if I can predict what should be the phase relationship in some delayed time, then that's called temporal coherence. And the spatial coherence tells you how clean the emitted surface is. For example, if there's a point source at infinity, it produces a plane wave in the near field. And so it has very good optical coherence, or spatial coherence, sorry. And when it passes through a distorting medium like scattering in a glass or through air, then the phase relationship slowly decays and you have partially coherent light, spatially coherent in the sense. And temporal coherence essentially is a measure of how pure the light source is, that how monochromatic it is. If it's a single frequency, then they all have a single wavelength. So if you have interference, they do not decoherence, and they produce a very clean fringe with good contrast. But if your light source that you're using interferometer is an ensemble of different frequencies, then the interference patterns, the bright of one may be the dark of the other because of different lambda scale. And so your contrast may quickly wash out. And that's an issue with the coherence. But you'll see that even with the low coherence, you can build what are called white light interferometers, albeit the interference pattern is visible over only the coherence length. And they're useful for some purpose. We'll discuss that. So let's have a brief on the various types of interferometers. So the best one that all of you would be aware about is a Michelson Interferometer. Here it's a, strictly speaking, you should call this Twineman green interferometer, because when Michelson built it, he built it with incoherent light. There was no laser at that time, so he used a sodium vapor lamp to do the measurements. So the enhancement to use a laser with the Michelson setup was by Twineman and Green for various measurements and displacement measurements. But for reasons that Michelson was the person who came up with this optical configuration, it still is referred to as a Michelson interferometer. So the Michelson interferometer, the light source is divided into two parts. The one part is reflected to one mirror, the other is reflected to the other mirror, and they again are recombined to the beam splitter and fall on the screen, and you have an interference pattern. So this is a double pass interferometer because the beam traverses 2 times along both the arms, and if the 2 arms are identical, you can get interference pattern even for 2 small coherence lengths. And if your coherence of the light source is long enough, then the imbalance between the 2 arms also can be equivalent to the coherence length by 2. So the contrast will be still good. The other variation of the so the Michelson interferometer is a amplitude division wavefront amplitude division interferometer. It's not a wavefront division interferometer like the Young's double slit experiment. Here you're taking the whole of the wavefront of light, dividing it into 2 copies and interfering here. This is more optimal from an energy point of view than wavefront division interferometers. So most of the interferometers that are used in metrology and measurements are amplitude division interferometers, and so is Mach-Zehnder interferometer. So in the Michelson, you have a 2-pass, so which is not suitable if you want to do odd error measurements and transmitted wavefronts. So a variation of that is a Mach-Zehnder interferometer. Essentially, the beam splitter is which is doing the double role of both splitting the beam and combining in the Michelson. It's split out into 2 physical interferometer components. So the laser beam is divided into one part and the other part. They traverse 2 along paths, and again, on another physically different beam splitter recombines them to produce the interferogram. So this is this configuration is referred to as a Mach-Zehnder interferometer. Similar type of interferometer, but where the beam traverses a circular path, is called a Sagnac interferometer. And here you have 2 modes. One along the you can have 2 sets of interference patterns traveling in one direction and the other direction, both producing interference patterns. And this kind of a circular or ring interferometer is called the Sagnac interferometer. And purely because it exhibits a Sagnac effect, which says that if the interference pattern is existing inside the Sagnac interferometer, and if the physical interferometer is rotated, the interference pattern is stationary with respect to the stars. It's inertial, at least stationary, so it can be used to measure rotations to great accuracy. So all your gyroscopes, optical and laser gyroscopes, work on the Sagnac principle, and that's the basis of the Sagnac interferometer. The other configuration is to use a physio interferometer, where a light source is collimated, and a beam splitter is inline and serves also as a reference flat. So part of the beam is reflected from the back of this reference flat, and the other portion is reflected from the test surface, and they both are reflected back by the beam splitter and interfere on the imaging system. So this is a standard setup that's used in optical testing of components. And when we come to the optical components or mirrors that are used in LIGO, phase shifting interferometer of this kind, or physio interferometer of this kind, is used to qualify this optical element, provided you know the quality of the reference flat. So the typical technique is to have a couple of interference patterns of different phases, and since the coherence length is large, you don't know the order of the fringe. So given a single fringe image, you cannot reconstruct the whole profile of the object. So you can phase shift by moving the reference mirror, reference flat by a small step and acquire multiple wavefronts, and then use it to calculate back the phase shift at every point. And even then, the phase is cyclic in pi. So you need to do phase unwrapping so that you can reconstruct the whole phase shift of the object and the profile of the object from the wavefront that you measured using the interferometer. So this is a technique which is called phase shifting interferometer and forms the basis of any phase shifting interferometer that's used in optical component testing, available from various commercial companies like LIGO and 4D for optical testing. One other application that's useful in physics interferometer is wave meters, where the light from the light source that you want to calibrate for the wavelength is expanded and collimated, and the reference plate of the physics interferometer consists of a tilted plate and a step wedge of multiple sizes, which produce an interference pattern of different varying frequencies. And from these varying frequencies, you can calculate what kind of a wavefront, what kind of a wavelength gave rise to that kind of a measurement, and that's the basis of a physio-based interferometer for wavelength measurement. And even when the coherence length is pretty small, you can use white light to form interference patterns for profile measurements. With a conventional interferometer, you cannot do the order measurement or the step height measurements where the continuity of the object does not exist. Whereas in a white light interferometer, you can do that precisely because the interference happens in a very small band where the coherence length is valid. And the zero order is purely dictated by the white light interference, which is exactly at the center. So these interferometers are built as part of a microscopic setup, and the interferometer is minuscule with a couple of slides which are added to the objective. And one of the slides serves as a beam splitter, and another is a small speck in the middle which serves as a reference flat. So light from the objective is split by the beam splitter, reflected from the reference and goes to the objective, and the other part is reflected by the object, and they interfere inside the microscope, and the image is as seen on the CCD camera attached to the microscope. And these are used in profiling applications, both in microlithography and for micro feature measurements with very great accuracy. The ready example for a multi-beam interferometer is a Fabry-Perot interferometer. Essentially, it's two mirrors with very high coatings, and if a part of light is incident, then multiple reflections leads to an interference pattern of a standing wave in the interference cavity. And whenever the wavelength matches the cavity's mode, or if it's integral multiple of lambda by 2, then it undergoes resonance, and you have a peak transmittance. And when it's off resonance, then the intensity transmitted by this pair of mirrors is very small. And so the transmission quality or the finesse is dictated by the reflectivity of the two mirrors. So for reflectivities of the mirrors at something like 0.2%, or say 0.2 reflectivities of 0.2, 0.5, and 0.9, you have a transmittance function for this pair of cavities, which looks like this. And so if you have a very high finesse, then this approaches almost a very narrow delta function. And this also can be used for both locking light to a specific frequency of the echelon mode for narrow line width locking of lasers, and also can be used for measuring the wavelength of light if you scan one of the mirrors, which is the idea behind a scanning Fabry-Perot interferometer. So one of the mirrors is mounted on a PZT, and if you scan it, you'll get a profile across the whole scan. And from that profile, you can measure what is the line width of your laser, because the interference pattern is scanned across the whole profile. And the intensity transmitted to the center is the transfer function of the Fabry-Perot. So this again is a reproduced graph in much more detail for finesse of different values. From 1, when the finesse is 1, it's just a two-part interferometer. It's just sinusoidal. As the finesse increases, there are more and more sinusoidal components getting added because of multiple reflections. And if finesse quickly makes sure that this multi-order interference pattern makes it a very narrow curve, which is there's a Fourier sum of all the signs that we sum up to produce an interference pattern. The Fabry-Perot cavity can be also used in a precision measurement application called cavity ring down spectrometer. Essentially, if you launch a pulse light source, the cavity traps light and takes a long time for the cavity to decay. And so this can be used in measuring the reflectivity of the mirrors. And there's a technique that is competitive to measure the high reflectivities of LIGO mirrors. So you launch a pulse light source, the light pulse that gets into the cavity oscillates back and forth because of the high reflectivity, and a small portion decays out. The output of this is an exponential, and the measure of the exponential gives you a value of about how much of the loss, reflective loss of the cavity is. And this can be used for measuring cavity losses as low as parts per billion for high resolution coatings. This is an example of a high stability ring down cavity that achieves a finesse of 10 power 4. So it has a ring down time of something like few microseconds, even though the input laser pulse is only a few nanoseconds. So that was a couple of interferometers of different types. Now let's look at a couple of slides on the interferometers and fundamental measurement. So everybody is aware about the Michelson-Morley experiment, where Michelson and Morley built an interferometer with multiple arms, multiple foldbacks to get a very long arm, and measured the fringe shift as the whole slab of glass, which is floating on slab of granite, which is floating on mercury, is rotated to orient along the direction of the Earth's rotation across the direction of the Earth's rotation, and repeated that every 6 months to see if the ether drift is apparent in the fringe shift. And this null measurement is one of the foundation stones to prove that GTR is right. And so the Michelson interferometer is an important experiment. Michelson-Morley experiment is an important experiment in the GTR system. Today, the whole Michelson-Morley experiment can be done in a more new avatar with very high resolution resonant cavities. You can have Fabry-Perot cavities with the finesse of the order of 10 power 12, 10 power 15. And today, the delta C by C error, the homogeneity of space can be done to an order better than 10 power minus 17. That's the limit to which it has been tested today, using a modern version of the Michelson interferometer, using very high frequency, high stability lasers and high finesse resonators. The Michelson interferometer also had been ubiquitous in stellar interferometry, where size of stars were measured using synthetic aperture construction. Here, essentially, you have a long baseline across which you collect starlight and combine to produce interference pattern. And from that, you can calculate the width of the star. The same thing is now used in a more modern fashion with optical gain in a PPLN, which is a periodically poled lithium niobate to increase the light output. And you can build a synthetic aperture interferometric telescope, which can have an aperture equivalent to the field over which the interferometer is set up. And this again is an interferometer technique to measure the finite size of stars and other things, which are very difficult to do with just a single telescope. Another experiment that uses interferometers is the Fermilab bolometer, which is an experiment in progress, which tries to measure the quantum coherence of location with unprecedented accuracy. So this essentially measures the correlation between two interferometers, one under the nested configuration, one in the opposed configuration, and see what is the cross correlation between them, and see if there's some quantum coherence between spatial distance. And last but not the least, the most important application of interferometry, as we have seen in the last decade, is in the measurement of the detection of gravitational waves. And LIGO is the instrument that is used to do that. So this is the optical configuration LIGO. We'll come back to it in a little great detail. So over the last couple of presentations on GW at home, you have now a fairly good idea about what gravitational waves are and how they're detected. So essentially, gravitational waves are quadrupular in nature. So essentially, this is an exaggerated simulation from ESA, European Space Agency. So as the gravitational wave propagates, if you have a uniform distribution of test particles, the space-time metric expands and contracts in a fashion that looks like this. So if you have so this is a differential measurement that you want to do. So initially, the detectors that were looked at were bar detectors. The idea being that if a gravitational wave passes through, the bar detector will be expanding along one direction and contracting the other, and in the next cycle, the opposite. So the idea was that if you have a large enough bar detector which is expanded and contracted by a passing gravitational wave, and if it is resonant with the mechanical mode of this bar detector, you can pick that mechanical mode in a resonant fashion and do measurements. So retrospectively, this looks quite bold given the accuracy, the detection sensitivity that you require. But this was what started the whole field of gravitational detection. And from bar detectors, people then built spherical detectors of various sizes. Many of them had been operational and some of them are still operating. The idea being that you borrow this idea, the bar detector is unidirectional. It can only detect gravitational wave in one direction of propagation and one polarization state, whereas the sphere detector, which uses much more modern technology like superconducting resonant cavities to measure the undulation of a neobium cavity immersed in liquid helium. And as a passing gravitational wave passes through, it distorts the sphere from an ideal sphere to make it elliptical along one direction. And this is an omnidirectional detector. And you measure the deformations using capacitive sensors. And but the interferometer bet all these techniques simply because the arms of the interferometer can be scaled up without having to physically build them as rigid objects. So we'll see how that happens and why the interferometer wins over the mechanical components like bar detectors and sphere detectors. So the basis of interferometer as a gravitational wave detector is essentially to use a Michelson with the two arms in such a way that if the gravitational wave passes through the plane of the display, then the distance between one mirror is expanding in one direction and contracting in another direction in one phase of the cycle, and the other way in the other cycle. And this differential measurement you do, will elaborate this a little bit in subsequent slides. And given the astrophysical sources that we are aware about, the best one being binary neutron star in spirals at 20 megaparsec, you need at least a strain sensitivity of 10 to minus 21. So if you have two test objects at a distance of a meter, the change between the distance due to a passing gravitational wave would be of the order of 10 to minus 21. So that's a very small, minuscule measurement that you need to do. And that is what makes the whole interferometer quite complex to achieve the required sensitivity. So we'll look at how a Michelson interferometer is a ready gravitational wave detector. And we'll again go take help of a GIF. So if you have a set of test objects sitting in a circle and gravitational wave is moving out of the plane of the display, this is how the test objects would oscillate. Though this is an extremely exaggerated picture, the actual oscillations will be very small. But what I would like to impress upon you is that when the vertical distance is expanding, the horizontal distance is contracting between the test objects, and vice versa in the next cycle. So this is not because the test particles are moving about, it's just essentially that the space between them itself is undergoing contraction expansion because of a moving gravitational wave across the plane of this display. So if this is arrangement of the test objects, and as the gravitational wave moves, they expand and contract. Imagine that we are able to place one test mirror of the Michelson interferometer and the other test mirror of the Michelson interferometer with the beam splitter in the center, and as the gravitational wave passes back and forth, this mirror moves forward, or not the mirror, the gap between this mirror and the beam splitter increases when this is decreasing, and vice versa. And that is what is used to measure the Michelson interferometer. And we'll see how that can be enhanced and what level of parameters and what values you need to be able to detect that kind of a minuscule change of 10 to minus 21. So this is a typical Michelson interferometer. The advantage with the Michelson interferometer is that when Lx and Ly are almost equal, the small phase noise in the laser and small fluctuations in the intensity of the laser is lost, and the common mode noise is small, and only the differential error between the two arms is measured, and that's the big advantage, especially when you build large interferometers. And as you saw, because of the quadrupolar nature of light, the gravitational wave does produce a differential error in the two arms. As Ly is expanding, Lx is contracting, and vice versa. And this is the strength of the Michelson as a gravitational wave detector. So one of the so if you have an arm length of L, then the displacement that you want to measure is multiplied by L. So you want to build pretty long interferometers, and that's why the LIGO interferometers are a kilometer class interferometer, so that you can measure displacements which are much larger. Because if you have a meter, it's delta L by L. If you have a kilometer, then it is a factor of 1,000. 4 kilometers is a factor of 4,000. That's why you have to build long interferometers. But at 4 kilometer or 10 kilometer, you'll reach an engineering limit. So one way to increase this limit or increase the length effectively is to use a Fabry-Perot technique. So if you can add mirrors on either side of the arms and use them in resonance, so because of the finesse, the laser beam undergoes, and under resonance, the laser beam undergoes multiple reflections back and forth, and you get an effective arm length that is a multiplication of the physical length into the finesse, effectively increasing the arm length and increasing sensitivity. We'll do a small numerical calculations to assure you that the gain from each of these can lead to a sensitivity that matches the requirement for an astrophysical source of 10 to minus 21, 22 that you need to measure. So this comes at a kind of a penalty that you have a slightly decreased bandwidth of the detector because the delay line has a longer time. But then the wavelength and the bandwidth of interest is in the shorter band length, where less than 1 kilohertz, where the reduction is hardly noticeable. So this is a technique that's used for doing that. The smallest change that you can measure from a gravitational detector is limited by the short noise or the quantization of the light in the cavity. So this is a measure that comes from the total light that is incident inside the interferometer. And since the LIGO interferometers are biased to operate in the dark port, all the laser beam is reflected back to the laser. So one way to increase the intracavity light is to put back all the light that's going towards the laser back into the cavity. We'll discuss this a little further in the down. And the signal sensitivity is of interest is in the bandwidth of few hertz to few kilohertz. So gravitational waves are propounded to travel at the speed of light. So the wavelength are in the order of few kilometers, to thousands of kilometers, in fact. So given the fact that the wavelength is in thousands of kilometers, a 4-kilometer arm length, even with the finesse, is hardly far away from the lambda by 4 Yagi antenna length, or the phase accrued in each pass is very, very small given the quadrature. So in principle, you can put the signal back into the interferometer to accrue more and more signal, and you can have a higher gain of signal compared to the common mode part. And we'll look at that also. And this comes again at the expense of the low frequency gain being reduced, but that's fine. So but at a larger bandwidth increase in the intermediate interest to the gravitational physics people. So let's do a small numbers game, just to give you an idea about what steps and how much of these techniques can improve the sensitivity to reach the 10 power minus 21 kind of strain measurement that they require for gravitational wave detectors to be able to detect gravitational wave sources. So if you have a strain sensitivity requirement of 3 into 10 power minus 24, which is what is the target design for advanced LIGO, for a 4-kilometer interferometer, this works out as a displacement measurement of 10 power minus 20. So this interferometer should be able to measure interference displacement of displacement measurement or a differential change in the two arms of the order of 10 power minus 20 meters, which is again an extremely small number. And so typically when you have laboratory interferometers, you can measure a nanometer very easily. The wavelength of light which I use in these interferometers, let's say it's around 1 micron. So you can quickly get lambda by 2, because even if you do fringe counting, for every movement of this mirror by lambda by 2, you will get one dark fringe going to one bright fringe. So if you do fringe counting and just use a count of fringes, then you can measure the location of the mirror or the differential change to an accuracy of lambda by 2. So lambda being 1 micron, you readily get 500 nanometer, which is a pretty large accuracy for mechanical applications. And that's why interferometers start out with very high resolution even for small powers. So if a laboratory interferometer can achieve 500 nanometers just for pulse counting, if I can do digitization of the wavefront and do the smallest intensity change, I can easily get a factor of 1000, because I can digitize to 10, 12-bit accuracy. I can get a nanometer measurement with a typical laboratory interferometer that's used for displacement measurement for qualifying mechanical systems. So this smallest intensity measurement is limited by the total power that I have for doing a small change measurement. And a typical laboratory interferometer has 1 milliwatt, whereas the LIGO can push up to 200 watt. So if I just use the factor of intensity of light, I have a factor of 10 power 5. So that's my first gain that I have, because the intensity used in the interferometers of the order of 10 power 5 higher, I in principle can detect the smallest change of light from the dark fringe by order of 10 power 15, 10 power 5 better than what I can do for a laboratory interferometer. So that's a gain of 10 power 5. And as I mentioned, the parts of the recycling mirror where the interference pattern, the LIGO interferometer is biased such a way that the output is the dark port. So all the light goes back into the bright port towards the laser. So you can use a recycling mirror or a power recycling mirror at the right coating or the right finesse to put back most of the power into the interferometer. And this gives you an enhancement factor of 10 power 2 again, if that's the finesse of this complex cavity. So the whole of the interferometer you can imagine as if it's a single mirror, and that mirror with this power recycling mirror forms a Fabry-Perot cavity. The finesse of that gives you that. For example, for the advanced LIGO on the O3 run, the input power is 40, and with a PRC of 40, you get a total power of the beam splitter to be around 1.6 kilowatt, and the intra-arm cavity to be 220 kilowatt, which is a huge gain over the 240 watt that you put in, and that's a sizable gain because of power recycling. So the other thing that you can do to improve the sensitivity, as we discussed earlier, is to improve the length of the cavity. And you can improve the length of the cavity by using the Fabry-Perot enhancements, as I mentioned. The Fabry-Perot enhancements essentially, you add mirrors in the two arms, which are resonant for the wavelength of light that's used in the interferometer. And that resonance leads to the light propagating back and forth multiple times. And the measure of that bounce is given by the finesse. So if you choose a finesse of the order of 10 power 2 to 10 power 3, you get an enhancement factor of length of L by that value. So your displacement sensitivity improves by that value. So this is another factor of 10 power 3. And last but not the least, as I mentioned, the arm lengths are 400 kilometer because of the enhancement, if you say with the 4-kilometer interferometer and a finesse of 100. But the wavelength of gravitational wave was tens of thousands of kilometers. So even for the whole pass of multipass and through the Fabry-Perot, the signal has hardly acquired a very small part of the quadrature. So you can put back the signal multiple times to the interferometer. So if you have another mirror here, which has a finesse, and you treat the whole Michelson interferometer as a complex single mirror, and that is resonant with the single signal recycling mirror. And typically you can achieve a finesse of 100. So this gives you another factor of 100, which takes you to the required sensitivity. And that's how you get to a sensitivity that can detect 10 power minus 21, 22 for to be relevant for astrophysical applications. So this is a typical simulation for a simple Michelson. The simple Michelson is somewhere here, a flat measurement. At 200 watts of power, it achieves a sensitivity of something like 10 power displacement sensitivity, a strain sensitivity of 10 power minus 20 or less. And with the Fabry-Perot enhancements, it improves. With the Fabry-Perot enhancement and power recycling, it reduces the low frequency gain, but improves the sensitivity at some peak value, which is good because most of your sources are in this region. And with signal recycling, it flattens out a little bit. The sensitivity goes down, but at the increase of sensitivity at adjacent frequency values. So this is typically what is aimed for in advanced LIGO for detecting gravitational wave sources. So with this background, let's go over the optical layout of an advanced LIGO detector. So you have a laser beam, which is incident on the Michelson interferometer. So the input cavity mirror, this mirror is called the power recycling mirror. And so you treat this whole Michelson as one single complex mirror, which then is resonant with the PR. This is the folding mirrors. And the beam splitter splits it in two parts. And this is the input test mass, which is part of with the Fabry-Perot enhancement mirror. And this is the end test mass, which is part of the Fabry-Perot and also the Michelson mirror. So this is one arm of the Michelson, 4 kilometer long. And this is another arm of the Michelson, 4 kilometer long. And then you have the signal recycling mirror. So this comes from whatever we discussed till now. But apart from that, you have a couple of other components that go into the interferometer, which is the output mode cleaner, and subsequently we'll see an input mode cleaner. The output mode cleaner is required because though we put in a TM00 beam, which is a high purity beam, and that's the mode that you want to use for this interferometer because it has the least divergence, and that's where your gravitational detection happens. But because of the finite error of fabrications in these mirrors and all the multiple bounces that happens, power from the fundamental mode is shifted to the higher order modes, and those higher order modes may not be resonant for various of these SRMs and the PRMs, and may not have the required sensitivity for gravitational waves. So they essentially are considered as noise. So if you want to improve the signal to noise detection ratio, you want to get back only the TM00 mode on which the gravitational wave has been encoded, and get rid of all the higher order modes that has been generated because the power being shuttled from the TM00 mode to the higher order modes because of the finite errors, the optics. And that's done by this optical mode cleaner. Sorry, output mode cleaner. Apologies. Mode cleaner is nothing but again a Fabry-Perot interferometer, which makes sure that it is highly transparent when under resonance, highly transparent for the fundamental mode, and lossy for higher transverse modes, so that it has very low loss for the TM00. For all the higher modes are lost for the cavity, and what you get out is an enhanced output, which is the high purity mode for the TM00, which contains the gravitational wave detection code. So similarly, there's an input mode cleaner, and this input mode cleaner is required because however well you build a laser, there's a finite content of the higher order modes, and given the specifications that you want to achieve for the LIGO detectors, an input cavity is used to further filter the laser output to make sure only the higher order modes are attenuated to a large extent, and only the TM00 mode is present. So in some sense, this is the core optical set of the total LIGO interferometer, the advanced LIGO configuration. There are a lot of other optics that go in for alignment and other things, the thermal compensation, which I'm not touching upon here because we're only talking about the interferometer part. And this is the advanced LIGO detector, which we just saw as a schematic. This is a 4 kilometer arm length with the powers labeled at the configuration where it was an O1. O1, the laser used was around 25 watt, and these are the intercavity powers and the powers of the beam splitter because of the values chosen for the power recycling and signal recycling mirrors for the configuration that was used in advanced LIGO's O1 run. So the dark port is set such a way that you get something like 25 milliwatt output power only for detection in the photodetectors after the mode. So since the whole interferometer is, even a tabletop interferometer is highly sensitive to ambient conditions, so the whole of the interferometer has to be housed in vacuum so that both refractive index fluctuations and air currents and other acoustic disturbances which couple to air currents and the optical components cannot disturb them. So the whole optical layout is done such a way that they can be handled inside vacuum chambers, and the whole of the interferometer, the end test mass at this end at 4 kilometers length and the other test mass. So the rest of it is housed in optical vacuum chambers, and I will discuss that later when I show the schematic. So the PSL alone sits outside, which is in air, and the PSL is a pre-stabilized laser, which is a LIGO laser, and it sits in a clean room on an optical table, which consists of 3 parts: the oscillator, the preamplifier, and the path stage amplifier, which is used to generate something 200 watts of ultra single narrow linewidth frequency. The whole of the laser works with the oscillator starts out with a single monolithic crystal, which is called an NPRO, which forms a small ring laser. And from the Sagnac interferometer, you'll see that this can have 2 modes. So a diode laser magnet is used to make sure that this is operating only in one single circular mode, so it ends up in a single frequency lasing. And that's how NPRO works, and that provides the required narrow linewidth laser, which is then subsequently amplified in various ways. And to make sure this narrow linewidth laser does not drift, it is locked to a reference cavity using a PDS technique. And this PDS technique is ubiquitous to all of LIGO in terms of locking of each arm as we go about. So initially the laser is locked to a local reference cavity, then subsequently it is locked to the input mode cleaner and then the mirror arm lengths to match the frequency. So the laser frequency is suppressed to a very high linewidth. We saw that the Michelson Interferometer has a high common mode rejection. So in principle, the linewidth should not matter. But since we have Fabry-Perot enhancements, and the Fabry-Perot interferometers are coherent optics in the sense that the interference transmittance works only if the coherence length is much larger than the spacing. So we need very high coherence to be able to use the Fabry-Perot enhancements and the signal recycling and power recycling. So that sets the linewidth requirement for LIGO, and requires a very complex construction of the laser to achieve the required linewidth and the fast application. The advanced LIGO optics are pretty large mirrors because these are 4 kilometer long cavities, and the mode at the cavity is something like 120 mm diameter. So the mirrors are pretty large, or quite larger than that. They're 38 centimeters in diameter and 40 kg in weight to take care of the radiation pressure. And the coating has an absorption which are very, very small, 0.4, 0.5 ppm. These are very difficult to achieve, and that's one of the limiting characteristics for measurements. So if you want the cavity to make sure that your power is not shuttled to higher order modes or not scattered in low order beams, which can lead to this one, low order noise from acoustic coupling to the vacuum chambers. The specifications for the optics are pretty stringent. So the surface profile variation should be less than 2.5 nanometer over the whole 300 millimeter diameter aperture. But the central aperture where the beam footprint of the Gaussian is present, you need a specification which is better than 0.3 nanometer over a spatial frequency of less than 1 millimeter inverse. And the total RMS defect should be less than 0.125 nanometer. So this is a typical error phase map of a LIGO mirror from a typical measurement. And these are measured with the phase shifting interferometers that I mentioned, a commercial company. So even fabricating these optical components was not an easy task. These were techniques that were developed specifically for LIGO. In initial LIGO, this was developed by CSA Australia as part of the techniques of contributions to initial LIGO from the Australian group. And there was a new technique of Teflon lap polishing was developed, which has become a mainstay for high precision optics in various commercial applications. And this has been further improved upon by various commercial companies and are the basis by which most of the optics for LIGO are currently fabricated. The other technique that's used for finishing these optics to high precision is ion beam figuring, where you do atomic sandblasting to remove errors in the final polished figure to meet the required errors in the mid-frequency and high-frequency. So this is the spatial frequencies over which you want the errors to be, and the reason why you want to do that is because usually when you use optics in normal applications, you measure only the wavefront and you measure the scatter. You usually don't measure the mid-frequencies because mid-frequencies don't play a major role in these measurements. But in LIGO, if you look at the aspect ratio of the interferometers, the beam footprint is only 160 mm, whereas the arm length is 4 km long. So given that high aspect ratio, the mid-frequencies can produce low angle beams, which can then get reflected from the vacuum chamber, which is housing this interferometer, and can make it back to the interferometer, contributing to the noise. So that's why you have very high stringent control on the mid-spatial frequencies, which can contribute to this error in the measurements because of the acoustic coupling to the. So measuring these mid-spatial frequencies is not straightforward because most interferometers have something like 1000 pixels by 1000 pixels for phase shifting measurements. So the instrument transfer function is not required, doesn't meet the requirements for being able to do those mid-spatial frequencies. So in fact, one of the commercial company had to develop a high spatial frequency measurement to be able to meet the required specifications of mid-frequency measurement. So this is the latest interferometer that's used for mid-spatial frequency measurement, which is also part of the metallurgy tools for verifying the components for advanced LIGO. So as the fabrication happens, after the fabrication of the substrates, you need to do the coating, and the coatings need to meet specifications in twofold. One, they should not destroy the form error or the accuracy of the optical figure that was produced till now, and they should have the required reflectivities and low absorption so that they do not deform under the high power that they encounter inside the cavity. So initially, when these coatings were developed at CSIO, they were able to achieve high reflectivities, but had issues with absorption. So subsequently, these coatings are done by the LMA laboratory, where they are able to achieve the required flatness or uniformity, along with very low absorption. And they use a dual ion beam sputtering to do that. And this is the evolution of optics quality over the last decade. And it's improved to something like 5 nanometer peak to valley and meets the required specifications. So the absorption and the coatings are the limiting factors for LIGO today, and there's a hunt on for achieving better recipes for coatings, which you have seen a couple of talks earlier, the various activities that can be taken up for future LIGO applications. Having built this optics to achieve the required sensitivity, though we are not limited by the short noise, we are limited by the disturbance to the interferometer from the ground noise. The acoustic coupling and the ambient couplings are taken care by the vacuum chambers, but the ground does move at something like a few nanometers in the frequency band of interest to LIGO. So you need to isolate them, and you had a presentation, I believe, by Dr. Mansa Devi on the various isolation techniques and techniques used to isolate the optics of the interferometer. So the idea is to use both active and passive isolation, and 7 stages of these are used to achieve the required isolation. So part of the core optics has a 4-stage isolation, which is using suspended pendulums to isolate far away from the fundamental frequency. And to be able to use them, you need the last stage of this mirror is essentially a single monolith consisting of 2 fused silica blocks coupled with fused silica fibers, so that they behave as one single entity to reduce the thermal noise in the total assembly to meet the required noise limit on the test masses. So this assembly is one of the most complex assemblies. So as I mentioned, this cascade of suspensions add up in sequentially to give you the 1/f8 for 4 of them. So each suspension away from the resonance has a 1/f roll off. So you have 4 stages for the passive part, you have 1/f kind of an isolation for the passive part. And then this passive part is then hung on active suspensions. And these active suspensions further, so in fact, you have to look the other way around. The ground is isolated by the pre-isolators, which then handle the 3 stages of active isolation, which then hangs the 4th stage of isolation. I think you had a brief idea about that from the previous talk. So the mirrors are attached with this monolithic test masses are attached with this monolithic suspensions by edge bonding, and these are some of the techniques that will be developed in India to be able to do the assemblies in India and to achieve the required noise limits and match the LIGO configuration that they've been able to do there. So even the rest of the optics, that was the cord suspension was for the core optics. Even the rest of the optics has to be isolated so that the vibration coupled to the table does not disturb the interferometer and the components. So these are various kinds of interferometer optics isolation stages, some of them triple suspension, some of them double suspensions, depending upon the requirement at various stages. So unlike a typical interferometer where the optical table is floating and you have rigid components on top of it, here the tables are actively isolated, and on top of that, each optical component is passively suspended to make sure they have further isolation to meet the required mechanical noise isolation for them. So this is the active isolation stage, and this is how the whole assembly looks like. From the floor, you have a passive pier on which you have the pre-isolators, which is outside the vacuum, and then there are crossbars which go into the vacuum, and on the crossbars you have the active isolation stage from which the core optics is suspended. And this whole of this is encased in a vacuum, and the vacuum chamber is then pumped down to achieve the required vacuum for isolation of the interferometer from the phase noise from wavefront distortion. The rest of the optics are then mounted in horizontal tables, which go into the smaller cavities, which are called the ham axis modules. And the vacuum chamber around them looks something like this. And this is one such assembly inside advanced LIGO. And this is how the apex of the interferometer looks like, where you have the beam splitter and the input test masses, and the other end test masses at their extremes on either side, which are out of the building. So this is the total interferometer encased in the vacuum while it's in operating condition. So all the alignment and running the interferometer has to be done remotely. All the mirrors are actuatable and alignable, either using automatic actuation or the last stages are by electrostatic actuation. And you can align them. You have to align the interferometer and bring them to the sweet spot systematically using remote control setup. And the control room is the place from where you can work. Because once you pump down, you have no physical access to the optical components, unlike a tabletop interferometer. So that was a brief overview about the advanced LIGO. And as you would have realized, advanced LIGO is like those initial telescopes that were built by Newton and Galileo to look at the vicinity of Earth, the planets, and the nearby satellites. Similarly, the advanced LIGO is like a initial detector, and there's hope that the sensitivity of the detectors will grow large enough. And one of the first steps for the next generation is to build light sources which can go to 2 microns, silicon optics, and squeeze light sources at 2 microns, silicon optics, coatings, and everything. And this, I believe, was touched upon by a presentation by Suresh about possible future R&D programs that can be taken up for gravitational wave activity all over the world. So one of the first upgrades that's likely to happen is A+, which I'll talk about in the later part of the advanced LIGO project. One of the sizable changes to the next generation would be the Voyager, where silicon optics will dominate, and that's what I mentioned in the previous slide. And this takes you to a large number of light sources of gravitational sources, which are across the immediate sensitivity, and gives you a large ensemble of measurements, which allows you to do cosmology with the large amount of events that you can measure with the third generation detectors. So this is a typical roadmap that's usually present. So we are in the initial phase of advanced detector LIGO, and the third generation would take this step further, and then there are higher detectors planned in the future. So that was the overview about the advanced LIGO project, advanced LIGO detector. Let me now give you a brief about the LIGO-India project. I was asked that we give you a brief idea about what the project is about. The LIGO-India project is for the construction of an advanced LIGO detector in India. It's a collaborative project with LIGO US and India. And this will be a detector that we jointly built with the interferometer key components being contributed by the LIGO US and we contributing the site and the required project activity to build an interferometer observatory using the components identical to the LIGO detectors in the US at Hanford and Livingston. And the 4 institutes that are spearheading this at this point is IUCA from UGC and GCSEM, IPR, and RRCAT from DAE. And they are called the LIGO-India part, along with the LIGO US. They are responsible for realizing the Indian mode of the International Gravitational Wave. So I believe you would have already had a brief idea about why LIGO-India is important. You want to have as many telescopes as possible to improve the duty cycle. And all the more so because for LIGO-India, we are at a place where we are quite far away from the other 2 detectors, which forms a very large baseline. So it gives you a better pointing accuracy for electromagnetic follow-ups. And that's an important step if you want to do multi-mission investment. So there's a scope of the project. The scope of the project includes finding a suitable site, constructing the required observatory facility, building the vacuum system for the whole 4-kilometer interferometer, installing the detector components that are contributed to the LIGO US, and building the whole observatory with the interferometer, installing and aligning and commissioning the whole interferometer, and achieving the required sensitivity for the advanced LIGO design, and running them as part of the global network in science runs to generate science data for doing bachelor physics. Apart from that, one of the mandates of this project is also to do science outreach both at site and off-site. That's something that's been being done with great enthusiasm across the various institutes. A little bit of history. LIGO India is probably the 3rd attempt at, or probably the 4th attempt at building a gravitational wave detector in India. As early as 1990, IUCA and RRCAT, along under the leadership of Dr. Nalikar and the founding director of RRCAT, Dr. Bhalkar, including Professor Sajid Dhurandhar and Dr. P.K. Gupta, put together a proposal to build a 100-meter prototype to start some activities. Unfortunately, this didn't get funded at that time because of technology limitations. In 1995, there was a proposal by ASIGA, the Australian consortium, to build a gravitational detector at Perth. The idea was to participate in it in kind and contribution, like the CERN participation, and learn how to build kilometer-class interferometers to build our Indian one in the future. But this unfortunately did not get funded. So in 2009, again, there was an attempt to put together an Indian consortium, and Indigo was born. And the interest for this consortium was to build an Indian detector called LIGO. As events would have it, LIGO Laboratory decided to contribute H2 as a possible 3rd detector outside the US to Australia, and Indigo decided to participate in ASIGA's effort to put H2 as an Australian detector as LIGO Australia in Australia, and gain experience on it to come back and build an Indian detector called LIGO. Unfortunately, again, the Australian team could not garner the funding from the detector, and so LIGO Laboratory made a formal offer to India. And so in November 2011, LIGO Indigo, the consortium that was trying to put together LIGO India and LIGO, submitted a proposal called LIGO-India Project to the Planning Commission to have a preliminary look at the project. And we had an in-principle approval for exploring possible sites in India. So unlike other projects which are limited in terms of size, the LIGO project requires a pretty large site, and a unique site in terms of the orientation of the arms and also the seismic silence. So it was felt that probably identifying a site was the most important step even before the project sanction. So this was an activity that was started as early as 2012 and spearheaded by and coordinated by IUCA. And initially 22 sites were shortlisted, and out of which 4 were 4 prospective sites were chosen based on the seismic evaluation. And Tata Consulting Services was asked to carry out detailed evaluation, engineering evaluation of all 4 of them. And DAE constituted a site selection committee, of which shortlisted 2 sites, a primary site and a secondary site. So the site required is, as I mentioned, pretty specific. You need to have 4 kilometer of arm length and a patch of 400 meter by 400 meter at the corner station to handle the detector effects, and also the logistics of the rest of the vacuum systems and the infrastructure required for the civil facilities, and the required space at the end stations for the civil infrastructure and the vacuum chambers for the end stations. So, and also they have to be relatively fat and on seismically silent ground. So, as I mentioned, these are the 22 sites that were looked in very seriously, and out of which 4 were shortlisted. And teams from ICER, Kolkata, Ayuka, and IPR and RRCAT contributed to the initial seismic surveys of short term of a couple of weeks to make sure that the sites have the required seismic properties to be able to take them further before. So, based on the site selection report, the primary site was narrowed down to a place called Andhra, close to Hingoli district, close to Nanded. And this is the site that's currently has been acquired for the LIGO-India Project. So, this is the local district map of Hingoli. This is the orientation of the arm and the location of the district where the site acquisition will be done. And parallelly, once the site acquisition the primary site was shortlisted, Government of India gave the in-principle approval for the project to go ahead, and a formal MOU between DAE, DST, and NSF was signed in the presence of the esteemed Prime Minister of India, the US, and the acquisition of the land was initiated. The land or the site for the primary site for LIGO India has been acquired. It's something like 175 hectares. And this is the stone marking the location of the apex of the interferometer where the two arms meet. And you can see the 4 coordinators for the 4 lead institutes. The site that has been acquired has now been characterized for differential GPS in terms of accuracy of the arms, the topological survey, and the seismic survey is currently ongoing. And to provide detailed characterization, the baseline survey for the seismic noise of the site before the site construction starts. So parallelly, the construction wing of DAE DCSM has completed the preliminary design and the engineering design for the civil infrastructure. And what you see is a conceptual aerial view of the LIGO-India project as it will be constructed at the site. So this would be identical in every sense to the other 2 LIGO detectors in terms of the optical configuration. But in terms of the civil infrastructure, probably we are a little more luxurious in the sense that we added more of civil facilities to be able to house more students and more academic personalities to be able to use this facility better than what viewers are able to do. So with LIGO India coming into place, we'll join the other 3 detectors that are currently operating: LIGO Hanford, LIGO Livingston, Virgo, the European detector at PISA, and Kagara, the Kamakati mines, which is currently operating, which is a kilometer class detector. And I would now like to close this in with a quote by Michelson, who basically would be considered the best possible instrumentalist in terms of optical measurements. So I'll leave you with this quote, and I close my talk at this point. It's open for discussions, questions. Thank you. Yeah. So I'm starting to get a couple of questions from the coordinator on WhatsApp. The first question is, how is the phase shift measured in the detector? So let me go back to the. Yeah. So this is a question by Naresh Pai Sachdeva. So in the Michelson Interferometer, it's a phase measuring device in some sense, because the light that is incident from the laser beam is split into two parts. And what you see on the intensity, what you see on the screen is the interference of the beam reflected from 1 and 2. So if the two mirrors, L1 and L2, are exact, or the difference between the two mirrors, L1 and L2, is such way that the two wavefronts of light arrive at phase, then the screen is completely bright. And if one of the mirror moves out or the other mirror moves in, so that there's a relative phase error between them, and if that phase error is lambda by 2, then the whole screen goes dark. So for all intermediate phase values, the intensity will be some sinusoidal variation, and that variation is what we captured in this equation. As so this is the intensity equation that you can use to calculate what will be the intensity for various phases. So when phi is 0, the intensity is maximum, and when phi is 90, the intensity is 0. So it is purely an intensity measurement system. The phase is encoded on the intensity. But as you realize that the phase change because the gravitational wave is a very, very, very small minuscule number, because the wavelength of light is 1 micron, whereas the physical displacement is hardly 10 power minus 18. So where is 10 power minus 18 and 1 micron? So the actual phase accrued is very small. So to be able to detect that small intensity change is why you require such huge amount of power into the cavity, both with a high laser or high power laser of 200 watt, and then power recycling to improve that intra-cavity power. That was the first question. The second question is from Swarangi Saraf. Do power recycling mirrors create small fringes as they reflect the light path? Yes. So you have to align the interferometer such a way that the power recycling mirror is in resonance with the rest of the complex interferometer. For example, if I come to the yeah. So you'll have to treat the whole of the Michelson interferometer as one complex mirror, and you have to align the power recycling mirror that the fringes, you don't have small fringes. The whole thing is resonant as a single mode, and the whole wavefront has zero tilt, so that you don't see these artifacts. So that's part of the alignment activity. And only when not only is the interference, the alignment zero, in the sense that the wavefronts are exactly matched with no small fringes, and the length between the complex mirror of Michelson and this in resonance, only then the power recycling works. So that's the requirement. The next question is by Neil Vadodariya. Why do the advanced LIGO mirrors look transparent in your slides? They do not appear to have any anti-reflection coating. Yeah. So if I go to the slides that they're referring to, so if you're referring to this slide, this is just a substrate without the coating. Why after the substrate has been completed, the substrate is undergoing inspection to the intermediate stages of fabrication. So if you want to see it with the coating, yeah, so I don't seem to have a slide with a coating. So what you see here as pinkish is not a coating. The dielectric coating has a tinge which has different colors, and this dielectric coating is designed for 1 micron. So it will be almost transparent for visible, except for a few tinges of different violets. The pink color that you see is a spray-on coating called first contact, which is used whenever the vacuum system is opened to prevent the actual dielectric coating being contaminated by ambient particles. And just before the pump down, this pink coating is peeled off. It's a very special polymer called first contact, which peels off atomically clean, taking away any residual dust from the coating. So the coating is a dielectric coating. So if you make a dielectric coating at 1 micron, it will be almost transparent to the visible, except for a few visible tinges, which is because of high frequency reflections also. The Swarangi Saraf, is it necessary to have two mirrors of the interferometer at 90 degrees? Yeah, it's not exactly, so you don't need to have the two interferometers to be exactly at 90 degrees. They can be at small angles, 80 degrees even. If you look at Virgo's configuration, it's not 90 degrees, it's a small angle, I think. It is slightly smaller than 90 degrees, I guess. The reason why you want 90 degrees is that the gravitational wave is a quadrupolar wave. So if you have an angle that is less than 90 degree, what you'll get is a projection vector of the strain of the wave. So you have a slightly reduced sensitivity. So if your engineering limitations requires that the 90° be 89° or 88° or 91° or 92°, the loss in sensitivity is not much. But if you intentionally build a detector which has an angle of something, let us say 40°, then you're losing a sensitivity because the projection angle that you get approved is small. So that's the level of accuracy that you want. So the 90° is not. It's just that at 90° you get the best possible projection and you get the best sensitivity whenever the antenna pattern matches the orientation of the gravitational source. The next question is by Nayan Gupta. How can undergraduate or postgraduate science and engineering students prepare themselves so that they can work at LIGO-India when it is ready? Yeah, so Ayuka runs a lot of science outreach programs and also projects where you can do MSc projects and MTech projects or BTech projects at the end of your course, or even be an intern. We are building an offsite facility at RRCAT where which can serve as a training facility in the future. So you can keep checking out the LIGO India website. These offers will be made available on the LIGO India website. I would suggest that the LIGO India or the LIGO project itself is an extremely multidisciplinary project. So there is work for every discipline from any sphere of engineering or science that you want to do, except say biology, I believe. Even chemistry is there. For example, the air tap bonding requires special chemistry. The front-end coating requires special chemistry for protection and contamination control. For contamination control and mechanical, you need to do FTIR of all the solvents that are used for cleaning. So there's a lot of chemistry that goes in even. So save biology, I believe every domain of engineering and physics gets there. So choose for yourself what domain of activity that you want to focus on, do your course well, and then check with Ayuka's websites and other places and other core institutes also to see if you can do a project. Then move on to the offsite facilities and also the SURF programs that the LIGO US people offer. So I think the best place is for you to keep looking at the LIGO India website, where Ayuka keeps constantly posting opportunities for MSc and engineering students, BTech students to take up activity related to LIGO and participate in it in the future. The next question is by Charlie. Do you have to be extremely intelligent and smart to be able to work at LIGO India or other such mega science projects? Yeah, see, this is a question that is a global question. See, we had always portrayed that science is done by super intelligent individuals. That's never been true, because what we hear of science in the history is through biographies, autobiographies, and collection of anecdotal information and a lot of things, and publications also. But if you look at history of science to publications, you will see that science is a collection of a huge amount of work done by a large group of people. Many of them, if you want to call them intelligent or extremely intelligent or mediocre or whatever. But what goes in is a lot of elbow grease and hard work. Yeah? And so don't worry about this question of whether I'm intelligent, not intelligent. What probably is important is whether you're passionate enough to take up extreme activity, persevere enough to do frustrating work, because doing these kind of interferometers and aligning them and doing the hard work is extremely pedantic in detail and extremely frustrating. For example, even cleaning these components to achieve the required cleanliness, to put them in the interferometer alignment and do the vacuum system breakdown, it's not a trivial task. So if you are dedicated enough and you want to put in the required hard work, intelligence is a relative measure. So that's not something that worry about. It's a passion for wanting to do extreme instrumentation that should drive you. And as you would see, all large projects are now team efforts and not individual efforts. And that is reflected even in the large prizes that are given out. Most of them are team effort prizes, and hardly individual prizes. So I would suggest that you don't bother about those. The next question is by Charita. Apologies if I didn't spell it well. Yeah. How do you take care of outgassing of the beam tubes due to the ultra-high vacuum? Does this not contaminate the vacuum? Yeah. So that's part of the vacuum chamber activity. And so what is done is that when these vacuum components, including the beam chambers, including the beam tubes and the chambers when they're built, there's a stringent quality control on the kind of steel that is used. The steel itself is chosen that it has a very low hydrogen loading, because when arc melting is done, you can load a lot of hydrogen into the steel. So you need to, when you do smelting, you can load a lot of hydrogen into steel. So people would do multiple arc melting on the ingot to reduce the hydrogen loading vacuum. That is one way. So you choose your steel to have very low hydrogen loading. That's the starting point. Then when you're doing the rolling of the sheet and producing the various components, there are contamination controls which make sure that only certain kinds of coolants are allowed to be used for machining and preparing the sheets so that you do not contaminate it. And after that, there's a stringent process for cleaning all these components before they're welded. After welding, then again they undergo cleaning. And as a final stage, they undergo an air bake. The air baking ensures that the coating is the surface outgassing happens to a large extent in the sense that the top layer of water vapor is evaporated to a large extent and hydrogen is also outgassed. And a thin oxide layer is formed because it's baked in air. And it is believed that this oxide layer has a little bit of impermeability to both hydrogen and will reduce outgassing to some extent. Yeah, that's still not completely borne out the experiment. But after the whole interferometer is assembled, there are gate valves to isolate the beam tube, and the beam tube is then baked. It's baked for a couple of months at 150 degree to outgas them completely. And once the beam tube is outgassed and baked and outgassed, sorry, they are never exposed to the atmosphere again. So they're always locked. So when you want to install the components, no components are installed inside the beam tube. The beam tube is just empty tubes connecting the corner stations and end stations. All the components are installed, optical components that are installed in the chambers which are at the apex or at the end stations. So there are gate valves, UHV gate valves disconnect that can be used to blank off these beam tubes when you are doing work on the beam chambers. And after the beam tubes and the gate valves, there are very large capacity cryo pumps, which make sure that when you're reconnecting these chambers back, after even though you're pumped down, you'll have a high load of water vapor because after the vacuum pump down, you'll still have a load from the optics that has been installed. You cannot break the optics. And that water vapor is pumped down by the cryo pumps. So that these various multi-steps ensure that the outgassing in the beam tube and the related contamination is minimum enough to meet the required specifications, at least for advanced LIGO. Probably as we move further to next generation, you may want to add other kinds of things like NEGs or non-aerocool getters which have active pumping so that you can achieve better vacuum than what is currently there when you become vacuum limited. At this point, advanced LIGO is not vacuum limited. That brings us to the end of various questions that were asked. I hope I could give a flavor of how interferometer is an important gravitational detector and an overview of the optical configuration of advanced LIGO and the LIGO-India project. And if there are no further questions,